So free body diagrams are the diagrams that we've been drawing all along, save for last video, because we're considering multiple objects. So free body diagrams identify all the forces acting on an object, say our block on a surface that I've gone back to so much. Right, so we have gravitational force acting at the center of mass, Fg. We have a normal force because of that, which is equal in magnitude, so Fn. And perhaps we have something pulling on it, right? So that's a rope, so we have somebody pulling. And so that would be a force this way, which is a tension force. And let's say that the ground is not frictionless, so we have a little bit of friction. It wouldn't be that much. We have a little bit of friction here. Friction force. Anything else that could be going on. Somebody could be pushing it as well. So somebody's pushing it. Right, with their hands. I don't know how to draw a hand, it turns out. They're pushing it this way, and so that's another F. This Fp is push. This is a free body diagram. Free body diagram. And they are essential for finding out what you need to in these problems. It's essential that you are able to produce these diagrams because you can break things down into components, this being x and this being y, and you can find the net forces like what we've been talking about all along. So you're pretty familiar with what free body diagrams are. I just hadn't given them a name yet. But what I want to do in this video is talk about guidelines for creating them, because there's some things that students are tempted to do that lead you down wrong paths when creating these diagrams. So first guideline, and this seems trivial, but it's very important. Identify the body that you're concerned with. So which object's motion do you want to know about? Which object is the question asking about? There could be many things. There could be 3 cars, there could be a boulder and another boulder and something else happening, but identify the body that you are concerned with. Wow, it sounds like a crime scene. And there could be multiple bodies, but it's going to ask about them individually, and at least you need to solve for them individually with individual diagrams, right? So identify the body that you're concerned with. 2, well, I will say each gets its own diagram. Am I going off the page? Just a little. Alright, each gets its own diagram. Usually it's only one that you're concerned with. 2, label only the forces and consider only the forces that act on that body. Consider only forces acting on that body. Right? Forces going on all around. Your body might be exerting forces on other things. It most likely is. Like at least force of it onto the surface, which results in the normal force on it. You don't care about that force. You only care about the forces that are acting on your body that you're concerned with. 3, the forces that are acting on that body they act on the body at its center of mass. At center of mass. We talked about this a little bit. It's just the point on a body where if all of its mass were centered at that point and the forces act at that point, it would be the same, right? So treat the object as a point particle, in other words, as if all the mass existed at that one point. And then on your free body diagram, this might be a little picky, but it's really important, I think. So for the lengths of your vectors should match the magnitude of them. Vector lengths should match magnitude. And this is just relative to your other vectors that you've drawn, right? Because you don't need to draw a scale on your thing, so you have tick marks along the x and the y, but if you have a force acting on the x that is 50 newtons, and you have a force acting on the y, which is 10 newtons, it should be relatively 10 times shorter, right? So definitely represent them correctly on your free body diagram, which I sometimes call force diagram. Once you've done this, then you can begin solving your problem by considering the sum of the forces in the x. It's equal to whatever it is, right? So there might be full forces, force of the push was one of them in our diagram before, but there might also be components. So F T from tension, cosine, whatever the angle was, which we never identified because we were just drawing this really quickly, but there's some force from tension, right? That is at some angle, we'll say, which I just drew with a different symbol. But we've spoken to this and worked with this quite a bit over the past couple chapters. So there might be components, there might be full forces, but you approach it by taking the components, or the sum of the forces in each direction. The sum of forces in the x equals something, which is equal to the mass times acceleration in the x. And then, separately, I even like to draw a line. When I was a student, I would handle the left column and right column, because it's often x and y. Sum of the forces in the y is equal to some sum of forces in the y. Forces and component forces, which is equal to the mass times the acceleration in the y. That is your formula. You identify the body, you consider the forces only acting on that body, forces act on the body at the center of mass, the vector length should match the magnitude, you draw your diagram. Make sure you identify everything, label everything clearly and neatly, write down the magnitudes of, so your actual numeric quantities that are given, right on your diagram, it's helpful. And then once you got your diagram, you're off to the races. Then you separate your consideration of the x and the y. So you consider all the x forces, you sum all those up, and all the y forces, and that gets you down the road. We will mostly be working, we'll be working with an even mix of component types that sum in the x and y and none. So there'll be plenty of forces that are just at some angle, in other words, right? There'll be plenty, especially tension forces. They love to give you problems with tension forces that are at odd angles. The normal force isn't always straight up in the y. Consider if you have a ramp, right? You have a block on the ramp. The normal force is not just the opposite of gravity. It's perpendicular to the surface. So Fn, that's the normal force. right? Because the block is acting on the ramp in that direction. So it's always normal to the surface, right? And so the normal force could have some component of x and components of y, right? Lots of things can, because I'm assuming you would assign this your x and this your y. It's also possible to, let's see, can I rotate? It's also possible to just define convenient axes for problems that call for it and rotate, right? You can think of it this way. So for some problems that is helpful, and consider that the x, and this the y. You could do that. So we'll run through a bunch of examples next lecture. Next lecture is dedicated to just how to solve problems given F equals ma, given this concept of inertia, given equal and opposite actions and reactions. So to summarize, before we click off here, Newton's first law was the concept of inertia. So objects in motion stay in motion. Objects at rest stay at rest, right? And we learned that mass is a quantification of inertia, which is the willingness, if you will, of a body to move. Newton's second law is best stated in equation form. F equals ma. The sum of the forces is equal to the mass of the object times the acceleration of the object. Yeah? It's the net force, right? The sum of the forces, the net force. If the sum of the forces turns out to be 0, well, then it still has some mass, but the acceleration will be 0, so you don't get anything, any motion, and we're back to Newton's first law. Whatever it was doing, that's what it's continuing doing. And then Newton's third law was equal and opposite. Every action, every force has an equal and opposite pair force. Right? Every force. Not just the normal, even though that was our example. Every force. Right? When you kick the ball, it hurts your foot. That's proof of that. All right. See you in the next lecture. Please try to commit Newton's first, second, and third laws to memory here, but truly understand them. Think about the concepts. Think about inertia. It's a weird one when we first come across it. And think about this one, and try to convince yourself of that conundrum of why anything moves if every force has an equal and opposite pair force, right? All right, see you in the next lecture.